concentrate on the toy model. So I will first say about some features of quantum gravity based on generativity, then discuss four derivative quantum gravity. Maybe I did not put it here, but I will discuss some problem of ghosts from what we think in our group, in me and my collaborator. And then we discuss this fourth derivative, four higher than four derivative polynomial models, which Manuel already explained a little bit. Yeah, and then I go to back to the subject of decoupling, and we discuss what we can expect from decoupling in the higher derivative quantum gravity, which is an unsolved problem, but we have some certain expectations, as I said yesterday. So first of all, what you can read about the lecture of today is this, first of all, the same textbook as I mentioned yesterday, because there are exercises, and I think it's possible to learn subject from this book, at least at this level. Then there is a paper a very important paper by Fradkin and Setlin, when they introduced the idea of effective quantum gravity in one of the appendixes. And in general, I used to say to my students, this is probably the best paper of on quantum gravity in till now. So then there are this concerning effective quantum gravity. There are two original papers by Donoghue and many reviews and lectures by John Donoghue and his collaborators. Then I will discuss here this paper, recent paper with Wagner. And then if you want to learn more about quantum gravity, you can read this dozen of review articles in this handbook on quantum gravity, because Cliff Burgess and John Donoghue were editors, and they invited other best people in this area, to best, I mean most well-known people in this area, to write this contributions to this book. And there is also a book on living review of generativity by Cliff Burgess and other sources. So it's now a popular subject. However, let me say that my opinion about effective quantum gravity is not exactly the same as of Donoghue and other people. So I will not discuss fully the differences, but some part I will. So first of all, what means how goes renormalizability in quantum gravity? We need two parts always. One is what is called covariant renormalizability. So you start with certain covariant action of gravity, can be action of generativity or other, with higher derivatives, with non-localities, with whatever you want. And then you find that it is invariant under this transformation, the diffeomorphism invariance, or in traditional way, general covariance. So it means that the action satisfies this Ward identity. And you can prove that this Ward identity is satisfied also. This is not an identity, but it's satisfied also at the quantum level. Historically, they did not put the last version. I inserted here one more transparency, but it did not did not come to here. So actually, I cite here only this our paper with Professor Lavrov, but it is the last paper. The first one was by Kelly Stella in '77 with the proof of renormalizability. But it was literally applied to four derivative quantum gravity. Then there were papers by Voronov and Tutin in '81, '84, which were like intermediate. Then there was a recent paper by Barvinsky, Blas, Sibirikov, and somebody else whom I don't remember. They did general analysis of renormalizability in gauge theories and in quantum gravity. And in this paper, we did, I think, most general, because we used this Batarin-Vilkovsky anti-bracket technique and proved covariant renormalizability. It means this identity for all kinds of theories, including non-local gravity models and whatever. So let us assume that this is true, because this is true. And then the divergences which you have in the given model of quantum gravity depend on the power counting. How you do power counting? So this is the main formula. Here, D, capital D, is the so-called power counting. So for logarithmic divergences, it's just 0. For power divergence, it's 1, 2, and so on, and positive. For finite terms, d is negative. So if we are interested in the divergence, are interested to set capital D to 0. Small d means the number of derivatives in the external lines of the diagram. So, and here on the right-hand side, you have RL is the number of momenta in the denominator of the propagator. Okay, so if you have Einstein gravity, you have RL equal to 2. If you have 4-derivative gravity, RL is equal to 4, and so on. N is the total number of vertices. Okay, and finally, K nu is the number of derivatives in the given vertex. So if you have cosmological constant vertex, then K nu is 0. If you have Einstein-Hilbert action term, and then K nu gives you 2. If you have 4-derivative theory, then you have vertices with 4, and so on. If you have 20-derivative actions, then there are vertices with K nu is 20. Now, L int is the number of internal lines, P is the number of loops, and N, as I said, is the number of vertices. So this is what people call, this is the so-called topological relations. If there are students, so I suggest just to prove it by induction, so it takes minutes. So this is this relation. This relation is also not very difficult to obtain. So like in our book with Bookbinder, he wrote very pedagogical way to get this thing, and many other books too you can find. So let us apply these formulas to gravity models. We start with the Einstein-Hilbert action, and then combining these two formulas, it's an easy exercise to get this relation. Remember, capital D is 0 for logarithmic divergences. So the number of derivatives in the external lines of the diagram, which correspond to covariant counterterms, is this. So at one loop, when P is equal to 1, you have 4 derivatives. It means that you have these 3 terms in the counterterms. And this was actually found by Hoften, Veltman, and one by Deser and Nevenhuizen in 1974. If you have 2 loops, as Gabriel and Manuel explained to us, then if you have 2 loops, then you have this set of counterterms with 6 derivatives. And interesting that if you use Gauss-Bonnet topological invariant, then this combination, independent on the coefficients, goes to 0 on shell. In pure gravity, if you have matter, okay, doesn't matter, external matter or quantum matter, then this is not true, of course. But in pure gravity, this is 0 on shell. However, this last term is non-zero on shell. This shows that the theory is not renormalizable. Actually, to see that the theory is renormalizable is perfectly sufficient to use this formula. Now here in this room, there was a few months ago a lecture by Zvi Bern, and he said to everybody and then to me in the discussion that this result of Gorov and Sagnotti, confirmed by van der Ven later on, is ambiguous actually. Okay, I don't know. I still did not read this paper which he mentioned. Maybe, but it's closer to your interest because I use amplitudes to evaluate. Anyway, I would not take it too serious because, first of all, we know that there is matter. And so one loop is perfectly sufficient. Then we have this formula. Even if it's ambiguous, so the theory is anyway non-renormalizable. But of course, it's quite interesting. Because I remember the time, like in '84, when people really thought that gravity is so special that maybe it will be renormalizable on shell in all loops. But 40 years after, I would say that it makes no much sense. So how we can go, what means the theory is non-renormalizable? It means that at one loop, you need to remove these divergences. You don't have them in the classical action, so you have to subtract them anyway and impose renormalization conditions. So you need at least 2. Each independent renormalization condition is an experiment, requires an independent experiment. So you need 2 experiments to fix things. At 2 loop level, you have like 2 dozens or 1 dozen of coefficients. You need 12 more, 10 more experiments. At next loop, you need 100. And so the number grows up, and so the theory has no predictive power. If we consider this as fundamental theory, if we consider it as effective theory, then we basically don't care about all these terms. So they appear, they are local, they don't contribute to non-local effects, infrared effects, so we just ignore them. This is different philosophy, let's say, different approach. Now, however, if we want to have renormalizable gravity, the simplest way is to include 4 derivative terms. So your theory includes Einstein-Hilbert term with the cosmological constant, and these 4 derivative terms, which is square of the Weyl tensor, square of the scalar curvature, and Gauss-Bonnet term and Box-R. Formally, all these terms are required for renormalizability. And in this case, the power counting is quite different because you have 4, so at most you have 4 derivatives, minus 2k2. It means that if you have, you may have 2 vertices with Einstein-Hilbert, okay, and then it becomes 0. Number of derivatives, you have only cosmological constant divergences, and minus 4k0, it means that if you have 1 vertex from cosmological constant, then you are done. You have 0 divergences, 0 derivatives in the contour terms. So theory is perfectly renormalizable. Together with the statement about renormalizability, covariant renormalizability, which was proved by Stella in a very, very good paper also. So things look at this stage very good, yeah? But it was understood even before and very well explained in the paper by Stella that this theory has some problem. And this problem is the problem of ghosts, which Gabriel explained to us in many details and many examples. So what means ghost? If you write the propagator with 4 derivatives and you can split it in this way, there is a possibility to introduce auxiliary fields. And then you see that this theory has 2 degrees of freedom. This is spin 2 part. Spin 0 part is similar. You have 2 particles. You can interpret this way at least. And one particle is has 0 mass and positive kinetic energy because overall sign is positive. But second particle has huge mass, proportional to Planck, and negative kinetic energy. This is called ghost. What means ghost? If you have ghost alive, real particle with Planck mass and negative kinetic energy, it's not a good thing because remember that we all know from classical mechanics that any system has a dream to go to the state with the minimal action. And action is kinetic energy minus potential energy. So if the kinetic energy is negative, as it is written in many books on classical mechanics, starting from Landau-Lifshitz, I think maybe also goes there, then this particle only wants to accelerate because it goes to the smaller action. When it accelerates, it becomes, according to the formula, mc square over square root of 1 minus beta square, it gets more negative energy or less energy. Okay? So what happens is that you can avoid this if you are in the isolated, closed system, okay? Because you have conservation of energy. However, if you have gravity, nobody can be isolated. This is a very important point to remember. If you have gravity, nobody can be isolated because each particle is perfectly capable to create its own gravitational field. So if you work with the S matrix or amplitudes in gravity, then this is, from the very beginning, not perfectly well-defined framework, because you may get a lot of information from this approach, but it's not logically consistent because in the asymptotic states, in the in and out states, you assume that you have particles which are free. And in gravity, you cannot be free, okay? You cannot be free in gravity. So this means that the ghost, if you have one single ghost alive, it will accelerate, emitting positively energetic gravitons, and then will accelerate until its energy becomes infinite. And then it will collapse the world. Yeah, exactly. As I said several times, you need one ghost alive. So this does not guarantee that you have ghost alive. It means that the spectrum of the theory has ghosts. But it does not guarantee that your theory is that there is ghost alive. For example, we know that there are top quarks. They were discovered in the in Fermilab, in Tevatron in '94. But in this room, there is not a single top quark. Okay? There is no top quark in this room. And in this building, there is no top quark. In this city, there is no single top quark. Because in order to get top quark, you need to go to the Tevatron or to other big accelerator. So the presence of the particle in the spectrum does not guarantee that you have this particle alive. And this is very good in case of ghosts, because otherwise we could not finish this lecture, for instance. So the question is, of course, from the side of the conservation of energy, you always can have the following. You have Minkowski space, everything is peaceful, and suddenly you create this ghost from the vacuum, and the huge number of gravitons or small number of gravitons which compensate, and the energy remains zero. Because in the Minkowski space, you have zero energy. Some people think that this is very bad, because you can do it. Yeah, you can do it. It does not contradict the conservation of energy. But as I will show you after, it contradicts something else. Okay? Some 10 years ago, I used other arguments. Now I will use this one. So first, this indication that this theory may produce instability was done by Ostrogradsky in this work of 1850, which is remarkable because, as far as I know, this is a unique paper which is cited as paper from 19th century. Okay, at least I don't know other examples. Then there was very nice paper by Veltman. Oh.
In medicine, there are papers who are
in medicine, okay.
and also in bacteria.
Right?
In bacteria.
Yeah, because
one of the most cited papers about how to cure diseases from horses. And these are from this.
I believe you, yeah. I was once in Visoza University, Federal University of Visoza, and my friend Afranio showed me a real researcher, not like me or him. There was a cow, and this cow had, we call it in Portuguese, valvula. I don't know how to say in English. Okay? And researcher, real researcher, comes and put his hand inside the cow. So after that, I believe everything about veterinary. So it's quite serious. So Veltman considered the scattering of massive ghost, very heavy massive ghost, and some light positive energy particles. And he has shown that the dominating process is this. So the normal particles get more and more positive energy, and the ghost accelerates, which is basically the same thing as I described. And it's complicated. I think it was his first paper of Veltman. And it was very complicated technically, but the output is this one. So at the quantum level, ghosts produce violation of unitarity of the S matrix. What this wording means? It means that if you form in-states, initial state, without ghosts, then there are interactions between gravitons, and you create ghosts in the out states, and your S matrix is not square matrix, it becomes rectangular matrix, which cannot be unitary, let's say. So the problem reduced to what I said before. Is it true that the bunch of gravitons can create a ghost? This is a non-trivial question if you think about that. It's a completely non-trivial question. Okay? I personally think the answer is completely negative. Okay, as I will show you after. So now, so as I said, the unitarity in general is not a well-defined concept in quantum gravity because there are no in and out states consisting from free particles, because nobody can be free. So what is really a criterion of the consistency in this case? In my opinion, it is the stability. So we know that for derivatives, as Ostrogradsky wrote many years ago, in four derivative theory, the solutions can be unstable. So we can just see for the classical solutions like cosmology, black holes, and see whether there is stability or not. This started from these papers because in Starobinsky 83 papers, there was an analysis of this situation, and he found that there are no growing modes in the theory with four derivatives. Then there was this paper by Hawking, Hertek, and Real, our paper with Anna Pelinson. Actually, we published a little bit later, before, and Hawking cited us. And then we had this with Felipe Sales, which was very close. But finally, final thing to understand our opinion was this in this paper with Felipe Sales. So what is an idea? So we just took, because black hole perturbations are very complicated. So I know a few people who work with them. It's not for everybody. Like me, I tried to learn this and I failed. So I spent some months and it's very technically complicated. So I finally gave up. But in cosmology, perturbations are simple and Giulio Fabris taught us how to make it. So so we just took cosmological perturbations in the theory with 4 derivatives and see if 4 derivatives produce instabilities, you would see some explosion. If not, you will not see some explosion. What we saw? If we take the initial seed of the cosmological perturbation below 0.44 of Planck mass, then there is no growing mode. So everything is very peaceful. The initial perturbations goes to 0. There is no explosion. But if we put initial perturbations of half of the Planck mass, then we have something which can be interpreted as an explosion of the perturbations. This means that there should be some protection to create a very high density of gravitons, okay, in the universe. So let's think about this again. In order to take the ghost out of the vacuum, ghost has the Compton length of the Planck order. So you need to concentrate gravitons with the density of the Planck mass. How you concentrate technically gravitons with the density of the Planck mass? There are experiments with electromagnetic field. People put many lasers, even in Tomsk. I am from Tomsk. There were high energy institute, and they did it. And they tried to concentrate a lot of electromagnetic energy in a small place to produce controllable thermonuclear reaction and have energy for free. And we know that this is not easy. And recently there was a paper by Luis Garay from Madrid, and he said the following, that if we try to organize the collapse of creation of black hole, putting a lot of electromagnetic field to the same place, they show that this doesn't work because this high concentration of electromagnetic field by Schwinger mechanism start to produce particles like electrons. And this evaporates. And finally, at some point, the black hole does not form because it does not come to the necessary density of energy with gravitons. How you will put all these gravitons in the peaceful, like Minkowski plus something, environment with a Planck density? Remember, Planck density is not a black hole. It's much, much more than that. First of all, it will start to produce particles. Then it will collapse and become a black hole. And the game changes. So my opinion is that in the peaceful environment, you simply cannot create ghosts from nothing. At least my intuition based on general physics.
This argument you are saying applies only to massless particles. You have massive particles you cannot disapprove. Not you can create black holes.
Oh yeah, of course you can, but not you cannot with good observation. But with massive particles, you cannot create the density, Planck density, because their Compton length is much greater, many, many orders greater. Okay? Good. So one more argument. Aye? Maybe. Okay. No, I believe it. Okay. Yeah. So the question is, maybe we can create ghosts out of vacuum in the different environment when the gravitational field by itself is huge. Let's go to the very early universe. And in this case, we have the following situation. This is the equation we got with Felipe Sales. And you can see that here, the wave vector of the gravitational perturbation comes always with this nice combination. So it is momentum in the co-moving frame divided by the A of t. A of t is a factor of expansion. And this is quite interesting because with a very huge in the very early universe, the universe is expanding. And it is expanding very fast. So with Patrick Peter, we did some continuation. We just took this explosion and tried to look what happens. And we found that, yes, at the beginning there is an explosion, but then this Q becomes smaller. When it becomes smaller, it starts to decrease. So the general shape of the curve is like that. So anyway, you do not create a ghost from the vacuum because your time also must be, remember that it's 4-dimensional density and the time is also Planck. So you need to create a ghost and it must last for some time. And during this time, the universe expands so much that there is no space for ghosts, the perturbations die. I don't know. Maybe you can explore this issue, okay, but not now, probably. Okay, so yeah, so there were also some objections because when I showed this in some conference 5 years ago, Richard Woodard started to say this is all because you work with the first-order perturbations, and some people took it seriously, like Alberto Salvio and us. And we took this following. We took Bianchi-1 universe because it's like gravitational wave with a zero wave vector and made it non-perturbative. And the result is exactly the same as for gravitational wave. So, and also I spoke to mathematicians, they confirmed it to me that if some system is stable under linear perturbations, then with a sufficiently small amplitudes, it is stable at the non-linear level. There are some exceptions from this rule, but not expected in this case. So this is the situation with ghosts. So maybe in this way we can have some answer to the problem of ghosts. Maybe not, I'm not sure. But I'm not completely satisfied with that. So it would be quite interesting to have theory when ghosts are controlled by some real mechanism. And for a while we don't have it. So one attempt was done by Manuel, Jose Luis Lopez, and me in 97, 96. So we introduced more derivatives and had this super normalizable theory of quantum gravity. Our expectation was original, that we can make only one particle of the spectrum to be ghost, and the mass of the ghost is infinite. But it doesn't work, because if you have like real spectrum, then the signs alternate. So it means that if the first particle is a graviton with A0 positive, then the second particle is ghost, A1 is negative, then the next particle is positive, normal particle, with mass heavier than the ghost, and so on and so forth. This brings us to the paper by Hawking in 80s. The title was, "Who is afraid of higher derivative ghosts?" And he said that you cannot work out these two terms as independent particles. They must be taken always together. But everybody with whom I spoke at that time, of quantum field theory people, I will not say names, said that this is strange because we don't have quantum field theory for two particles. Okay? And now I would say that basing on this, we have more chances because here we have one massive particle and another massive particle. So it's quite natural that they will stay together, let's say. So all these models of quantum gravity, they can be reduced to this if we are thinking about propagator. So you have two form factors, not quantum form factors, but classical, which you defined from the very beginning, and there are these phi and psi functions. And at least for polynomial functions, phi and psi, you always have, you can expect supernormalizable gravity. the polynomials must be of the same order, okay? And you are for sure have ghost or ghost-like states, better say, because there may be complex masses. And if you have like transcendental functions, as Manuel showed yesterday, then at 3 levels there are no ghosts. But if you take into account loop corrections, you always get infinite amount of ghost-like states. Okay? Yeah, I have paper if you want to look to the title is Counting Ghosts in the Ghost-Free Series. So it is proven. I think it is proven, at least nobody complained at the time and now. So, but remember that everything what we discuss corresponds to the situation which starts from the Planck scale and goes above. So physics, all physics we are interested in happens below Planck scale. So it means that we have to be interested, starting from inflation and whatever you can imagine, well below Planck scale. And in this case, we can just maybe we can ignore 4 derivative terms whatsoever. And this was the proposal of Donahue in '94. This is an idea of effective field theories. So the question is, if this is true, if the fundamental theory is one of those, I mean with ghosts, okay, and difficult to imagine how this can be avoided because the question is how to deal with ghosts, in my opinion. There are other opinions, okay? But in principle, at Planck scale or above, you probably have something like that. By the way, if you take string theory, then string theory also produces exactly the same 4 derivative terms. And these terms are removed by the transformation which was invented by Zweibach in '85. And this transformation requires infinite amount of fine-tuning, so it's difficult to consider it as a real solution of the problem. So I would say that with respect to 4 derivatives and higher derivative terms, string theory is exactly on the same situation as any other theories of quantum gravity. So if we have these massive things, and then at low energies, we won't use this effective gravity, then Donahue's main statement was that universal theory of quantum gravity at low energies, means below Planck, is quantum gravity based on Hilbert-Einstein action, means generativity. But this is not obvious, because for this you need to have the decoupling of massive modes. And this decoupling of massive modes is completely non-trivial in gravity, because remember I showed you yesterday that the decoupling of poor loop of massive mode is guaranteed. But there are mixed loops. There are loops which have one line of massive massless field, I will show on the next transparency, and another line of massive field. Does it decouple? It's not obvious. If, of course, it decouples in the sense that you may expect that this massive loop collapses and gives you the Snell diagram. Good. But the question is, the remains is exactly like generativity or is other theory, like those which I showed you yesterday of the type of R, 1 over box R, or R mu, 1 over box R mu. So in 2008, I wrote a paper called Polemic Notes on Quantum Gravity. I just said that it's not obvious because these guys can perfectly well appear in the infrared from this decoupling. And so now, recently with Wagner, who is here, we made and investigated this question, but not in quantum gravity, and in this model, which is called model of Antoniadis-Matola. This very nice model. It has 4 derivatives. It has non-polynomial interactions, which is important because gravity has it. It admits effective theory in the infrared, and so it is looks like a very good model. So actually, this model was proposed by Adinsov and me 1 year before, but Antoniadis and Matola made a real model out of it with quantum calculations and so on. So what is the model? It's like that. So here you have 4 derivative terms, okay? This, and this, with, without extra exponentials. Here we have something which comes from the Einstein-Hilbert term. It means this guy comes from Einstein term, and this from cosmological constant. Here we have exponential non-polynomial interactions. So originally, this section comes from the integration of anomalies, something which I showed you yesterday, but with a flat metric G bar, this fiducial metric. So the coefficients are like that, which is not important for us. This is the formula for this coefficients, but this is a minor point because we will just treat these coefficients, gamma, lambda, theta, and zeta as arbitrary. So this is the fundamental theory for us. Very good. Then what is the effective low energy theory? Effective low energy theory means that we believe that at infrared, in the infrared, these terms are irrelevant because they are Planck suppressed. So this is the effective theory. This can be seen in two ways. It's part of the Einstein-Hilbert action, okay, with a wrong sign, okay, which is good to put wrong sign here because anyway, it's toy model, okay, because it's positively defined. Or you can see it as a scalar field, normal scalar field, lambda phi 4 with another parameterization. It's important that it's massless. So we just have, the first step is to calculate one-loop divergences. It's simple. Heat kernel calculation can be done easily. And this is the result for the fundamental theory for this, okay? And this is the result for the infrared theory. So what is our expectation? Remember the lecture of yesterday. We expect that what remains from this theory in the infrared will fit with what appears from this theory in the ultraviolet. And the ultraviolet, since it is massless theory, is completely controlled by this formula 2, because this formula 2 is divergence. And divergence controls the logarithmic form factor. Okay, so we expect that what remains from the form factors from this theory, this is only divergence. The form factors are huge, pages of formulas. So will fit very well with coefficients, with everything, with this theory. And this is what happens. So let me show you some details. So this is the beginning of the game. We can put cosmological constant, and then we have light, small cosmological constant, light field instead of zero mass field, which is just for generality. Then we have these two propagators, light field and heavy field, and vertices. I put here only one line of heavy field, but there can be unrestricted number of them, of course. And so, in the tree level, we know that this propagator collapses to the point, and there is no propagation of the heavy mode, and the light mode continues propagating. So what about one-loop contributions? We have these three diagrams. This diagram is supposed to survive in the infrared. This diagram is supposed to decouple quadratically in the infrared. And this diagram, we don't know. Okay, let us see. All the game is to explore what happens with this diagram. And in this paper, we could do it with Wagner. So, yeah. Actually, other diagrams, which may be somehow relevant, are like that. Two types of snail diagrams. We know that they contribute to divergences, but they do not contribute to the form factors. So in principle, they are interesting only when we compare the form factors with the divergences. But they are not interesting when we compare form factors of one theory with the form factors or divergences in effective theory, okay? And then there is a tadpole, which we basically did not take into account, if I'm not wrong, okay? Wagner can correct me if you want. Okay, so if we are lucky, if the general relativity is really universal theory of quantum gravity in the infrared, as Donahue suggested, so then everything will fit, and we will see the connection between this formula, the generalization of this formula, and this formula in the infrared limit of the first. Good. So the calculations were done in the following way. So this is the basic formula. The correction to the one-loop propagator of the external field has some self-energy parts, which look like that. And the form factors are quite complicated. They are constructed because there are two masses, especially. So they are constructed from these several notations you need, A, B, C, D, and capital A. So, of course, logarithmic divergences are always controlled by just in-dimensional regularization by omega. And so the formulas, as I said, are huge. So I give you only one, which is shortest one of these sigma functions, which is this. So you can see that this is quite complicated. But if we start to make an infrared limit or ultraviolet limit, everything simplifies rapidly. So this is the situation when we took limit of p square going to infinity. You see that these sigma functions became simpler immediately. And we meet here as already logarithmic form factors and non-logarithmic terms, as expected. Now, as I said, what we could expect in the infrared, what we could expect in the ultraviolet and infrared. In the ultraviolet, we expect these logs to fit ultraviolet divergences calculated with the heat kernel. And in the infrared, and so in the ultraviolet, we expect always perfect correspondence between minimal subtraction and momental subtraction schemes. Why? Because, as I explained to you yesterday, in the ultraviolet, you can always reduce the problem to the loop without masses. Masses become irrelevant. If you have loop without masses, then you have log which goes just together with divergence. They're not separable. Okay, so you have to have some correspondence. Now, infrared is completely different because in the infrared we have these two relations. We can even simplify things a lot by setting small mass equal to 0. It means we have 0 cosmological constant. Good. So those are more simplified things with small m square equal to 0 and already in this limit with heavy m. So we have 3 self-energy parts, which got quite simple. So we have here things like log multiplied by P4, which means 4 derivative divergences. And we have other situations with P4 and so on. And we have some small non-logarithmic terms too. Good. So by the end of the day, the qualitative result was the following. These mixed diagrams becomes tadpole, snail. Okay, so it stops producing form factor exactly as expected. This is good. And so moreover, we found, actually Wagner found, perfect correspondence with the ultraviolet minimal subtraction calculations with the heat kernel in the ultraviolet. And we found perfect correspondence, most important, in the infrared with the divergences calculated in effective theory. It means that our effective low energy theory remains effective low energy theory if we take quantum effects into account. Everything is according to our expectations. I would say that there are some subtle issues to explore further, but in principle, the main question was answered in this model. This model has some hidden secrets, I would say. So we did not even discuss this yet. Okay? But in principle, I think we can extract more information. So, So for example, this is this sigma gamma square, okay? And it just, if you just take everything simple, then you have exactly this, and it fits the ultraviolet. It fits the ultraviolet because there are P4 and so on. Let me say that here I show you only the corrections to the propagator, but in the paper you can find the corrections to the 3-point function and 4-point function. And they also provide the same good fit with effective theory. So basically we have, like in this model, we confirmed the idea of Donahue that general relativity, that effective theory, which is effective in classical theory, remains effective theory in quantum at quantum level, at one loop level, which is nice. Now we can go to the next part of this lecture and ask the following question. Okay, let us trust this. Let us believe that in real quantum gravity with 4 derivatives, of course, we can take more derivatives, but it will require more calculations. We have effective quantum gravity, Einstein gravity, as an effective theory. So what we can expect in this case? Something similar to what we have in the Antoniadis and Motola model, or something different. And I will try to convince you that we have to expect something qualitatively different. It's not the same thing, because gravity is more complicated theory than the Antoniadis and Motola model. And the difference is the following. When you quantize gravity with 4 derivatives, you need to introduce this kind of terms. This was introduced first time in this paper of Radkin and Seitlin, which I mentioned. So the total action after the Dewitt-Fadeev-Popov procedure includes the action of quantum gravity, which is, in our case, 4 derivative, gauge fixing term, and Gauss term. Gauss term is more or less not interesting, but because it's massless, so it does not go to this heavily contribute to decoupling. But the gauge fixing is completely non-trivial. Why? Because I can, if my quantum field is phi mu, or this phi lambda mu, quantum metric, then the gauge condition has arbitrary parameter beta 1. And the weight operator, which is here, must be of the second order in derivatives. Otherwise, you do not remove degeneracy of your class action. And you don't have a well-defined propagator and things like that. And this weight functional also has some arbitrary parameters. For practical calculations, we used to choose this beta 1, beta 2, beta 3 to reduce everything to the minimal form of the operator, which means, as I showed you yesterday, we have typically the h mu alpha beta equals to delta mu alpha beta with some coefficient a1 box square plus a2 g mu g alpha beta box square plus 3 more terms. So we typically use beta 1, beta 2, beta 3 to remove these 3 terms and make calculations simpler. This works very well in the heat kernel approach. In diagrams, I'm not sure, I don't know, but okay. So you have at least 3 parameters. But in principle, your result may depend on these parameters. Now, on top of that, you can introduce ambiguity, arbitrariness, into your parameterization of quantum field. And it was done in the most general form in this paper by Gonsalves, Tiberio de Paoloneta, and me. So you see that here parameterization has 6 parameters. So you have at least 3 parameters here. Actually, you can put more, I think up to 6 also. And you have 6 parameters here. You have a lot of arbitrary parameters. The question is, remember that at one loop, the result is depends on the up to second order in quantum field expansion. So this is all ambiguity in the parameterization. This is the most general parameterization. In this paper, we had even more general because we introduced some conformal ambiguity. I will not discuss it here. So we have a set of arbitrary parameters. The question is, our results in the fundamental theory with 4 derivatives and in the effective theory with 2 derivatives, how it will depend on these parameters? Because if, for example, all these parameters enter the game, maybe we can modify the coefficients in the effective theory and there is nothing to compare with in the infrared. Or in the ultraviolet, we can expect that it may happen that you will have nothing to compare in the ultraviolet. And remember, we need a fit between infrared and ultraviolet. In some sense, we need to have some trajectory which connects the 2 regimes. Okay? And it might happen that there will be nothing here to compare with and nothing here to compare with. Let us explore this. The first thing is to make calculations. But these calculations, for the Einstein-Hilbert theory, it was done in this paper. You cannot make it more general. But in 4 derivative theories, it was never done, and it was really big exercise. So it's difficult to do. And do we need to make this calculation to understand what we can expect? No. We can make the analysis based on general theorems of quantum field theory, because we work on quantum field theory, and quantum field theory has some general statements. So it was proved, starting from the paper by Arefьeva, Fadeev, Slavnov, 73, and then by many other authors, including us with this paper with Lavrov, which I mentioned, that if you have one loop divergences of effective action, which depends on alpha I is the set of all these parameters, beta 1, beta 2, beta 3, gamma 1, and so on. Let's call it alpha I. And then we have another set of the same parameters. Let's call it alpha 0, which is like this, which you use to make calculations simpler, or any other fixed choice. So the difference should be always proportional to the classical equations of motion. To the classical equations of motion. In Einstein-Hilbert theory, the classical equations of motion are like this. Okay? In different theories, it may be different equations of motion. Okay? And this is perfectly sufficient to explore the possible ambiguities in these theories. So up to some extent, it's not, you can do it without calculations. In quantum gravity, the tradition is based tradition, I would say, well justified, that we never trust general theorems without calculations. We always try to make calculations, because sometimes very general, good considerations finally become wrong. We had some examples. Okay? But here, I would say it's not expected too much. What concerns decoupling, I don't know. Okay, let me show you how it works. Let's start with Einstein theory, quantum gravity. So quantum gravity based on relativity. So we know from the power counting, as I explained you, that the divergences are this, have this structure. So you have a square of the Riemann square, tensor square of the Ricci tensor, square of scalar curvature, box R, and cosmological constant. Equations of motion are like this. So we see that the difference is epsilon mu multiplied by f mu. What can be f mu? 2 plus 2 is 4. So if you want 4 derivative variation, you have 2 derivative equation of motion, then f mu should have 2 derivatives. Most general covariant 2 derivative expression is this one. It includes 2 differential operators with B4 and B2 coefficients. Here, B are numbers, and coefficient B3 with cosmological constant, and B1 and B2, which are just other coefficients. This is most general thing you can imagine. Of course, the values of these coefficients, B1, B2, B3, B4, B5, depend on these gauge fixing parameters and reparameterization parameters. Okay? But they can be seen as independent arbitrary coefficients. Okay? Then we have this expression for the divergences. It multiplies this f mu by equation of motion. Anybody can make it as an exercise, and you will see that the coefficients of these expressions in the divergences start to modify when we modify coefficients B, okay? And they modify in the following way. C2 changes to C2 plus B1, C3 to this combination, C4 to this, C5 to this, C6 to this, and C1 to C1. Why C1 doesn't change? Because C1 is a coefficient of the Riemann square. And in this expression, there is no Riemann square. This is only Ricci square. Some people make the following mistake, I would say. I was a referee of several papers with this mistake. They attribute C1 to the square of the Wild tensor. This is wrong. Why this is wrong? If you are young people, so maybe you will also write paper. Don't commit this mistake. Because Wild square term contributes to the gravitational wave. Okay? And Ricci square, which we have here, I made a wrong step. Ricci square, which we have here, okay, also contribute to the gravitational wave. So when you modify Wild square, you modify Ricci square. And only Gauss-Bonnet does not contribute to the gravitational wave. So this coefficient, arbitrary non-ambiguous coefficient C1 is the coefficient of the Gauss-Bonnet. No way to attribute this to C square. It is wrong. Okay? Because you may think, okay, C square is Gauss-Bonnet plus something. No. Gauss-Bonnet is the replacement of the symbol of universality, unambiguity, and whatever you want. And C square is not here. So, and you have another combination, this one, with the cosmological constant and all this stuff. This is also stable under the change of these numerous coefficients. So it means that in the quantum general relativity, there is no possibility to define the beta functions for the C square or for R square. They do not exist. Okay, they're ambiguous. You have beta functions well defined. If you want to make renormalization, you can do it, but only for the Gauss-Bonnet and for this guy. And this was done in Fradkin-Zeitlin in the same paper of 82. This produced the so-called on-shell renormalization group, as they called it. I will show you now. So once again, what we have in general relativity is only two parts are non-ambiguous. Remember this result which Manuel showed us from Hooft and Veltman, these famous coefficients 1 over 100 and 7 over 20. Both depend on the gauge fixing on everything and basically can be done zero. This was done by Kalash, Tarasov, and Tutin in 78, by the way, by direct calculation. First time, and then we did, and many other people. So, yeah, let's go to four derivative theory. In this case, situation changes a lot. Why? Because you still have the same set of divergences with four derivatives, but in this case, the equations of motion are also four derivative. 4 minus 4 is 0. So in this case, f mu of alpha is a numerical function. What is the numerical function you may have, okay, compatible with covariance? Only this. It can be metric multiplied by some numerical function of these parameters. So, in this case, we can say that the difference between two effective actions is proportional to f of alpha I, which is a completely arbitrary coefficient, multiplied by the, what I called in 94 in my best paper probably, the conformal shift of the classical action, okay? So this is a conformal shift of the classical action. What it means? It means that if we put here the wild term, you have 0, okay? You have 0. And so wild squared term has well-defined beta function. If you put here Gauss-Bonnet, 0. So Gauss-Bonnet has perfectly well-defined beta function. If we put here R squared term, we know from yesterday that it gives you box R. So R squared has perfectly well-defined beta function. Okay, but box R, no, it is surface term. You may say it's irrelevant, very good, but it doesn't have also well-defined beta function, which fits with our result on ambiguity of box R in general, in the anomaly. Very good. So we see that the level of ambiguity in four derivative theory, in infrared theory, the assumed infrared theory, Einstein gravity, is completely different. So, yeah, this is what we have in Einstein gravity. So we have, no, this is what we have in this four derivative gravity. So ambiguous part includes this and this combination of Einstein and cosmological term. So actually, you can have well-defined beta function for C square and R square. So let's go to renormalization group. In quantum general relativity, you have only one coefficient. It is this one. It is dimensionless combination of G, Newton constant, and cosmological constant. And for this, you have this famous renormalization group equation. It was found by Fradkin-Zeitlin in the same paper. So it's very nice. You can try to make some physics out of this. It's not easy to do. I would say nobody tried from this formula, but in principle, why not? But this is not. This looks like asymptotic freedom, but remember it's on-shell thing, and moreover, you have to remember that lambda gamma is not the coupling constant in the theory. So calling this asymptotic freedom is a very, very, very big exaggeration, for sure, because this is a parameter of the theory, but it's not the coupling constant. The coupling constant is related to G alone, because coupling constant is the parameter of loop expansion, okay? And cosmological constant is not the parameter of the loop expansion. So, is it possible to get here well-defined result? Yes. For this, you need to use this alternative construction for the quantum field theory. It's called Wilkowicki-DeWitt unique effective action. So the calculations were done first time by Taylor and Veneziano, and recently we did with Breno Ghiccini and Tiberio De Paolo Nieto. And actually, this paper was completely motivated by the referee. We sent it to journal, and it's first time in my life that the referee was really helpful. So referee said, you made big calculation, and it serves for nothing because you verify general theorems. Why you verify general theorems? But there is a part in your paper which I put in the last moment just to make it more nicer looking, which you should expand. So we split our paper into two, published another part with calculations in another journal, and here we have really good speculations, I would say. So, yeah, but it is Wilkowski-DeWitt effective function. It has nothing to do with normal quantum field theory. It's your choice. So you choose to use this scheme, and then you have everything which does not depend on gauge fixing, does not depend on this parameterization, and so on. Do we need to use Wilkowski and DeWitt effective function in quantum gravity? The answer is, if you like. So if we want to use Wilkowski and DeWitt approach to quantum gravity, we can use it, and then the story with the decoupling and so on and so forth will look completely different. Okay? I don't know how it will be. But let us forget about this and go back to normal quantum gravity. Then, for this theory with 4 derivatives, we will have this set of well-defined beta functions in the minimal subtraction scheme. And we have no, from my perspective, regardless in the literature there are other proposals, I don't see how in the momentum subtraction scheme it can be different. So this last coefficient, 5/36, was corrected from Fradkin-Zeitlin by Avramidis and Barvinsky. In original paper by Fradkin-Zeitlin, it was +1/36. And this is correct because it was verified by many authors, including us and then Roberto Percacci with several different collaborations and so on. So I would say this is very safe. And yeah, and I think it is quite a solid result for the ultraviolet. All these three equations, of course, this means asymptotic freedom for lambda. Lambda is the coefficient of the wild tensor. This is difficult to be called asymptotic freedom, but the formula is like that. So for Gauss-Bonnet, and for Xi, you have fixed points. So it's not my interest today to discuss it, but there is an ultraviolet fixed point for Xi. Good. So what we can expect in quantum gravity if we make the real calculations? We can expect that in the ultraviolet, form factors will reduce to these divergences, which I did not show here, unfortunately. So we reproduce these divergences which lead to these expressions for the beta functions. So form factors which we are going to calculate in 4-derivative quantum gravity, in the ultraviolet regime, will have logs, and logs will give us exactly this renormalization of these terms. In the infrared, we are not going to meet anything reasonable. We are going to meet a mess which will depend on the choice of parameterization and on the choice of gauge fixing. So it means that calculations must be organized in a corresponding way to see this mess. Okay? So just making calculations in one particular parameterization, one particular gauge fixing is not really helpful because we need to observe the mess. Okay? And yeah, and so this is the let's say forecast for the result of these calculations. As usual, this forecast may be confirmed or not. Maybe there is something which I missed, for example, in this analysis. Maybe, for instance, in the ultraviolet, there will be some extra terms. I cannot imagine how this can happen. But maybe it's the problem of my weak imagination, not of the real thing. In the infrared, I would say that it is safer, that we will have a mess. So the interpolation between effective quantum gravity and fundamental quantum gravity is supposed to work. let me say that in effective quantum gravity, you have also well-defined results, but these results are not related to divergences at all. For example, it is the interaction between two point-like masses, which Manuel has shown, and it can be calculated. It was done in a consistent way, in my opinion, by Dalvit and Mazzitelli in '97, and we corrected it a little bit recently. But in principle, yeah, and you can see that the result does not depend on all these arbitrary parameters, which is not owing to the scheme which Dalvit and Mazzitelli invented, very complicated. Not very complicated. You need at some point to take a test particle and go to the motion of the test particle. So I have time remaining, so I could actually put more transparency. So if, as I said, so if this expectation about decoupling is true, then in the ultraviolet we expect to fit with the divergences of fundamental theory. In the infrared, we should expect to fit with the results of the effective theory, but these results are ambiguous. And so, yeah, this last paper is what I said about '94 when I invented these things with F mu and so on. So, but this just was to explain the result of Fradkin-Zeitlin, because there just gives the result without explanations. So I wanted to understand it. Okay. So, yeah. So we can go to conclusions because my material is over. So, for today. So, what is effective approach? Effective approach to quantum gravity is a compromise because we give up from our main purpose. Our main purpose in quantum gravity is to solve high energy problems like singularity and so on. And we say, okay, we don't care about high energies, let's look to the low energies only. This makes sense because all physics occurs at low energies, because here high energies, as Donahue very well explained to us in the last decades, high energies is above the Planck scale, and this is like exotic for any physicist. So it makes sense, but we give up from our original project of quantum gravity to solve fundamental problems. There are other discrepancies with the effective approach, and so it is very, very interesting to have some well-defined results. So in principle, even this interaction between 2 point-like masses, the quantum correction is some 75, 74 orders of magnitude below the experimental abilities. It looks strange. Why we do it? Because it will be probably never checked, right? But this is true. But since people spend like more than 50 years actively working on quantum gravity, it would be interesting to have at least one physical result which we agree that this is correct. Okay? And unfortunately, we don't have it. Unfortunately, we don't have, even we cannot calculate in a unique way the interaction between 2 point masses, okay, correction to Newton potential, which is like strange, because this quantum gravity is very resistant theory. I think Pauli said in '50s that to quantize gravity, you need somebody very smart. And for a while, my impression is that this smart person did not come to us. So we don't have a single physical result which we could say, okay, this is correct. Okay, everybody could say, because I have one and somebody else have another. So yeah, this is bad news. On the other hand, there is good news that you young people have something to do. So that in this area, because there are questions, there are interesting questions to answer. One of these interesting questions to answer is that if you have this Dalvit-Mazzitelli result in our last version with Modesto and Tiberio de Paolo Neto, there is a combination of beta functions in the presence of matter, which is invariant under this change of parameterization and gauge fixing. The question is, we found that it enters the equation for the test particle. if you find another example in cosmology or whenever else, when exactly this combination comes to your classical equations, this would be very, very interesting, I would say. This would be the most interesting thing, okay? But at least for me. But for a while, we don't have even this. So once again, the decoupling is fundamental if we want to do effective field theory, because all the game is about what remains from the high energy theory with heavy degrees of freedom in the infrared when these heavy degrees of freedom decouple, and we have to see how they decouple and what remains. So yeah, so mixed diagrams are the key part because the simple diagrams with the same mass in the loop are elaborated, in my opinion, till the end, so it cannot be improved. So, and finally, we have this situation in quantum gravity. We know what to expect. Thank you very much. I can, but I need my laptop or something. It's paper with Modesto and me, I think the last one. If you go to Spires and find author Modesto and me and Shapiro, yeah, you will see it's like 2 or 3 years ago.
Okay. Can I, just to see if I'm understanding correctly, you're saying that because we don't have a gauge covariance and parameterization invariant way of checking all those divergences in the relations with the IR, we can't actually be sure of this 10 to the minus 74 scale that you're saying, because in essence, if we don't know what is the correct way of doing, maybe these corrections could go up, right?
No.
No?
No,
Why
no,
not?
no, no, no. So maybe I expressed myself in the wrong way. I can go take another transparencies and start to show you, but probably I will do it. So the idea is the following. There are 2 corrections, okay? Because you have V of R equals to minus G M over R plus something like x1 over R squared plus something like x2 over R cubed, okay? This term is the point of the main discussion because, first of all, it is perfectly well verified by post-Newtonian approximation. So you cannot change this coefficient because this means that you enter in contradiction with the real physics. This is something. If you trust that this term is there and the coefficient is not +2 or -2, I don't remember by hand. So then it means that quantum gravity should be forbidden forever, okay? But in my opinion, this term is 0 from quantum gravity. Okay, I can explain why. This term is very small, really, okay? And the last years, after this, my paper of polemic notes on quantum gravity, things go to the side that people start to agree that this is most interesting because this nobody wants to discuss too much. No, some people discuss, I'm wrong, okay? But this coefficient, when we calculate, okay, if we do everything correct, then it is related to the combination of these parameters, which is completely invariant. So we can calculate, I think, with Dalvit and Mazzitelli scheme. Okay, but I can explain you this part. So what Donahue calculated in the original paper includes 2 kinds of diagrams. This wavy line is a graviton. Okay, because he worked with effective quantum gravity based on GR. Then there is this diagram. And yeah, and maybe Gabriel knows the 3rd diagram. So, no, I think these 2. Yeah, exactly. Yeah. So this most traditional diagram. Yeah, you are right. I'm getting old, so I'm mixing. So Yeah, and of course the same with ghosts if you want. With ghosts, okay? Those diagrams are certainly have to be taken into account because we want, the first point is that you take this guy, okay, here is mass M1, here is mass M2, and you get this term. Okay, M1 is small and big, okay? And then you want one loop corrections to this. This is first which comes to your mind. Nobody complained against these diagrams. They should be taken into account. But there is another set of diagrams, like this. Okay, in the first paper, Donahue omitted this diagram intentionally and made a mistake with one of these diagrams and still got correct result for X1. Very good, but we show in paper with Jose L and Guilherme Pichot that if you omit this diagram, we use scalar electrodynamics, then the whole result depends on the gauge fixing. So it's not amplitude. So Donahue changed his mind, other people who calculated at the same time also, and they started to take all diagrams. And when they started to take all diagrams, they had some result. The question is, these diagrams should be included or not? My opinion, no. Because what we want is the interaction between two macroscopic bodies, M1 and M2. And they use scalar field. By the way, Iwasaki did this calculation in 23 years before Donahue. And he did this calculation with scalars, fermions, and vectors, without philosophy of effective gravity and so on. And he got different results for these three. This guy is equal, okay? But this gives different results, of course. So if we want to quantize, if we want to interaction between two macroscopic bodies, and we put this field in the internal line of the diagram, okay, we know that internal line of the diagram means that this field is a quantum field. This is classical source. Very good, because there is no internal line of the massive field. Here you have internal line of the massive field. It's game changer. It means that you quantize this macroscopic body as a scalar field. Like you want interaction between Earth and the moon, and you quantize the moon. And this is nowadays people are monotheists and so on. Things changed a lot from the old times. But in principle, moon may quantize you back. So, and it might give some back. It is, because internal line in the Feynman diagrams, Gabriel, I'm sorry. This is what Donahue said, yeah, we discussed with him. And so I invited him to this handbook project. He accepted. It was very, very helpful, and so on. So we are good friends with him. But this we disagree, because they say that they have some people did it. They used very, very complicated schemes and tried to show that this is equivalent to something classical, basically. Okay, I can believe it. But if things are presented in this way, I cannot accept it, because this is quantizing the macroscopic body. Okay, on top of that, if you take first papers, then they said that this is a first order or second order in H bar. And macroscopic body, the mass of the macroscopic body, even of one single proton, is already proportional to H bar, because mass of the proton is not the sum of the masses of the quarks. Masses of the quarks are responsible for like 4% of the mass. Most of the mass is what we can call conformal anomaly. So it is proportional to H bar already. So for me, and for Dalvit and Mazzitelli before me, this must be removed. Okay, and then we should work only with these diagrams, and then we have only this term, and the coefficient changes. I think this is the source of the whole discrepancy with the coefficient, maybe not. And then, if we work only with these diagrams, there is an interesting shift, because, first of all, you don't need diagrams. You just derive your divergences, classical divergences, quantum one-loop divergences, and you have things like C kappa omega mini, alpha beta log, okay, of minus box over mu square C kappa omega alpha beta plus other terms like this you recover from divergences, as I explained yesterday, right? Maybe it's better to put here just Ricci, because it's the same. Okay, for Gauss-Bonnet does not contribute. So you have R alpha beta, then you have R log over mu square R, then you have T mu nu, T alpha beta, log minus box over mu square, T R alpha beta, there are 5 terms, T alpha beta log minus box over mu square, or 6 terms maybe. T alpha beta, this is, because this is an external source, you can just take it as an energy momentum tensor of whatever you want and put there what you want. This is Dalvid-Mazitelli, not, okay? And then R, this I did. Okay, the last term I think is this R log minus box over mu square T, the trace, something like that. And all these terms come with some beta functions like beta 1, beta 2, beta 3, beta 4, and beta 5. Okay? All these beta functions depend on the gauge fixing. Very bad. But then you do the following. You calculate your contributions to the Newton potential with with what you call in cosmology Newton gauge. You have 2 scalar fields, phi and psi. You get your equations for phi and psi, go to spherically symmetric restriction, so you have only one coordinate, static, and so on. Simplify. And at the end, you have this coefficient, which I call x2, is the something like y j beta j. Okay? So this is a linear combination of these beta functions. Okay? And you have this for phi, okay, the phi, okay, is, and psi. You have two things, and this will be like y line prime beta. Still, this linear combination depends on the gauge fixing and on the parameterization. But then, Diego Mazitelli and Dalvid invented the following trick. Let's take one of these masses, big M, and another small test mass. Okay? And this test mass, they wrote for it the geodesic equation. And this geodesic equation is based on classical geodesic equation plus quantum correction. Since it is effective, you always must do it in the first order. When you do this, what happens? A miracle. Because you get your x1 is a kind of third combination, z, j, beta, j. And this combination is gauge fixing invariant. Okay? So then you get it. And when it is gauge fixing invariant, you can check that with these theorems and formulas, which I show you, exactly this combination should emerge. So it works. But the question is, okay, this works what I asked last, that this works for the test particle. Find some other physical situation when it will be the same combination. Would be, for me, it would be a big step forward, because maybe you find some place when this may be checked experimentally, because this is like, as David said once, 74 orders of difference with experiment.
That's exactly my question. How much can scheme depend on being a big mass and a small mass and all this? Because it seems like if I had choose big, small quantum if I have choose small quantum masses, things will be heavily dependent on gauge fixings and those kinds of stuff.
Absolutely right. So this scheme depends completely on this fact that we use test mass, because this is a unique example when we could go to the end, in my opinion. Mm-hmm. And so since we have other example, I would say it depends 100% at the moment.
Just make a...
Let's proceed to other kind of questions, because you are...
another person to ask a question after me. Professor, it's a very simple question, really. When performing that reparameterization there...
You should press the button because it doesn't work.
Yeah, sorry. Thank you. When performing that reparameterization where you choose to parameterize the value tensor, not the rich scalar coefficient, could we do the opposite and like not do the value tensor and change the coefficient of the rich squared?
Change in which sense?
When you were talking that you saw lots of referees making changes like in both those tensors, the coefficients when doing reparameterization.
Okay, I think I understand. You mean when I spoke about Gauss-Bonnet versus Weil tensor?
Yeah.
Square, okay. Maybe it's good to explain better. So, the point is that we have possibility to work in a different parameterization. Original parameterization, let's say, includes square of the Riemann tensor, square of the Ricci tensor, and square of R scalar curvature. But it is good to change to the following. Gauss-Bonnet, which is R mu alpha beta square minus 4 R mu square plus R square, and C square, which is R mu alpha beta square minus 2 R square mu plus 1 over 3 R square. Why it is good to make this? And then the third will be R square. The reason is the following. If I make the presentation of metric, as we discussed yesterday, the flat metric plus H mu, okay? Then H mu has basically 4 different fields inside. So you may write H mu as H mu 2 plus H mu 1 plus H mu 0s plus H mu 0 omega, which means spin 2 part, vector part, one scalar and another scalar. Now, vector part, which is spin 1, is poor gauge. You can choose gauge and this part disappears. If you think about just classical propagation. Out of these two guys, one is also gauge fixing dependent completely. And these two not. These two survive in principle. So, and moreover, C square completely defines the propagation of H2. And R square completely defines the propagation of this scalar. Okay? So in this representation, everything is very clean because Gauss-Bonnet defines propagation of nothing. C square defines the propagation of tensor mode. And R square defines the propagation of scalar mode. Now, imagine I can move this guy to something like shift the coefficient, okay, as I show you. So here we have some B2, and you can say, oh no, C2. C2, and you have C2 changes to C2 plus B2, for example, which is completely ambiguous. Then I have a choice looking at these formulas. I can attribute this to the change of Gauss-Bonnet or to the change in the C square, or to both. What is correct? The correct is attributed to C square. Why? Because when you change R mu square, this guy, you modify the propagation of spin 2 part. Okay? It is physical output. So your propagation of your field changes. Now, if you change the Gauss-Bonnet, propagation of your field doesn't change because this guy does not contribute to the propagator. And C square changes. And this is a physical thing, I mean, propagation of the mode. So when you make this modification, it means that you modify C square, but you don't modify this. So if you think that, like, because this guy is universal. It does not depend on the gauge fixing. But you can say, okay, this universality can be of C square, and start to make big physical speculations immediately, what people do. And this is incorrect, because actually this is completely dependent on this, because for the propagation of spin to mode, these two guys are completely equivalent. Okay, and this is different. So this is critical combination. This means that this guy is universal, and this is not.
Thank you, Professor.
Okay. I think I explained or not?
Yeah.
Any other question? So maybe you still want to ask again.
No.
Okay? So let's finish this section by thanking Ilya.
Thank you.
And remember that we reconvene at 2 for the short seminars, okay?
So at 2 we have 2 seminars of students, and at 3 we have the seminar of Gaston.